So let's continue. So that's the substitutability and the substitution function itself. So again, as I remark all the way through, these are all things that can be done programmable by a machine here. So again, we need to be a little bit more some paper. Okay, so section 334. So you want to think more about assignments or interpretations, right? So the point of page, what's the idea on page 55? Page 54, sorry, here is. If we want to look at a formula like this, so here's something in the language of arithmetic, right? Then what I've got here is this variable, and I've applied this prime function twice to it, and multiplied it times this constant symbol 0, and applied the prime function symbol to it. So the interpretation of this formula, right, in the natural number structure, let's call this phi, in, say, the natural number structure here, plus times 0 prime, and there should be, these are the real functions, these aren't just symbols. I won't always do these superscripts. So the interpretation of phi in the structure here should only depend on what we assign to v0. After all, it only mentions v0. What an assignment does to v1, v2, vn is entirely irrelevant. So if we've got maybe we've got two assignments, w0 and w1, and these are in, right? Recall that this is a function from n into, coincidence, we've got the same n's occurring, n into n here. And w0 of v0 is w1 of 0. So they assign the same thing to v0 here. Then we're going to have that phi under the assignment w0 is going to hold if and only if it does under w1. So just to use this notation. Because, as I said, they assign the same thing to w0, and what it does elsewhere is not germane to the truth or falsity of this phi here in the structure here. So there is a sort of, we just check that our definitions are good, right? We wouldn't want something like this to go wrong, right? What does the prime function do in this case? Prime is the successor function. So x prime is, I'm in x plus 1. So 0 prime, this is a constant symbol. This will be interpreted in the standard way as the number 0. The prime will be the successor function. So the interpretation of this in the natural number structure is the number 1. Sorry, off the page. Interpretation of this in the natural number structure will be the number 1. Yeah. If I'm sensible and interpret the 0 symbol as the number 0. Please, could you explain what the W0 and W1 are? Right? So this is defined there on one of the earlier pages. These are just functions from the natural numbers into definition 330. So W is just a function from the natural numbers into, it's just a function from the natural numbers into the structure, which actually in this case happens to be also the set of natural numbers. So W0 and W1 here map n into n. And then we use that assignment as in definition 331, right, to assign, well, objects in the structure to terms, but also ultimately here we're assigning truth values to a formula, this formula. So we're saying that this assignment is going to make this formula phi true in n, if and only if this one makes phi true in n. Because all the assignments talk about are, there's a relevant for this formula, all the formula talks about is V0. So it only matters what W0 and W1 assign to 0 here. Okay, hope that's okay. So the moral is, for terms, their interpretation only depends on the assignment of their free variables to objects. In the structure. So, and then again for formulae, the truth or falsity of the formula only depends on the assignments of the free variables. The free variables in the formula. I mean, again, to just kind of take a basic case, if I just take V1 equals V2, the simple atomic formula, right? And again, I take two assignments, W0, W1 here. Then the structure here will think V1 equals V2. will be this, right? So W here, this W, if I pick this W, it's going to assign something to V1 and to V2, right? If W0 of 1 is W1 of 1, and W2, so W1 of 2 is W1 of 2. So I've specified that W0 and W1, they assign the same things to V1 and V2. Right? V1 and V2 get the same value here. So then this will make the formula true in N if and only if the other one does. Well, I mean, in the example I've given here, I've specified that they're the same. So actually, they are true. So we have this and this, right? If I specified like this. Because in this assignment, I've just said that, sorry, no. This is if and only if. So in this assignment has given the same values to V1 and V2 as this assignment has done. Right? That's what I've specified here. Right? Right, and then the outcome about whether this makes this true in here will depend upon whether this equals this. Here. And so this is in this simple atomic formula here. But this is entirely, this is just a simple example. This is true for all formulae. Right? Just depends on what the valuation does for the things that are mentioned in the formula. This can't depend in some weird way. The truth of this equation in N can't depend on some weird way by what we assign to V126. Right? The only relevant data are here. So it's just saying things are clean, right? Things are working well. And that's what lemma 346 says. Right? So let's look at 346. I've got a structure, and I've got a term and a formula of the language. Now here I've got two assignments, W and U. And they have the property that they assign the same things, right, to free variables of V, free variables of T here. And then the conclusion is, okay, then the valuation of the whole formula under the assignment W is the same. Right? So how the term comes out here only depends upon what you do to the free variables. And here we saw an example with the phi, the equation, and n, the natural numbers. As long as the two assignments assign the same values to the free variables of phi, that's what's important for determining whether phi comes out true in M under that assignment. So if one of them makes it come out true, the other one makes it come out true, and vice versa. So in a sense, this is kind of intuitively obvious here. Actually, we can give a mathematical proof of this here. And I don't intend to do it because, I mean, to be honest, these things are not terribly interesting, and they're really quite lengthy. But here you can see an example of something that I just said, right? We had an equation, right, here. And what we've got here is that W makes this equation come out true. Well, this means the interpretation of this term and this term had better be the same, right, here. And because W and U assign the same things to the free variables that are there in the formula, right, that's going to mean that W star of S is the same as U star of S here. Right, so this equation holds if this equation holds, and then if and only if this U assignment makes the equation true inside M here. And now we just have similar clauses down here. Right? So this is W assignment is going to make this relation true of these gadgets, right? If and only if the relation R holds of the assignments that W engenders for the T1 up to Tn here. And if U and W end up with the same, assigning the same things to these terms, then this will be in the relation if and only if this is in the relation, if and only if U makes the formula true in M. And we have similar things here for negation and implication, and also for the universal quantifier here. Okay, I don't propose, as I say, going through all of this proof, but let's see what the other clauses of the lemma also say. Let's suppose I've got terms. Here's part of the assumption is that W actually evaluates or interprets S0 in the same way as S1. Then it shouldn't make any difference if in some other term T, I substitute in S0 for VK or S1 for VK. Because when I evaluate, then when I come to evaluate the result using this W, right, W of S0 is the same as W of S1. So this is going to make no difference. Right? When I come to evaluate the term, I have to evaluate the things that are inside the term. And the evaluation of S0 is the same as that of S1 by hypothesis here. So that's not going to make any difference to the valuation of the whole term. Okay, and clause C here is saying, if in addition, right, not only that S0 and S1 get evaluated the same, but now let's suppose they're substitutable for VK in phi. Now, according to our official definition, when I look at the valuation of that W assigns to the terms in this formula, and I see whether the formula is true in M, if W star assigns S0 the same thing as S1, and I substitute that in for the variable VK, it makes not a jot of difference as to whether the formula is true or false in M, because I'm substituting in the same thing, basically, here. Okay, so we can give that a fairly lengthy proof, right, which I don't propose to go through, but is there on the next page for each of these clauses here, if you're interested in reading those through. So basically, it's just saying, you know, things are kept, things work. It's kind of, it's all, the machinery works as we intend it to. Are there any questions there about that? Okay. So again, this is a definition you've already had. So I'll remind us of this. Formula is said to be universally valid, right here. It means it's true in all structures appropriate for the language and for all valuations. So it's saying it doesn't matter which structure I pick or which valuation, it will always come out true. So a typical example of a validity, universal validity, would be something that just says, you know, S equals S, right? An equation where the thing on the left is the same as the thing on the right. So it's not going to matter what assignment I make to the free variables of S to see how I interpret S, right? It doesn't matter what M is. This is always going to be true for any M and any W there. So of universal validity is sort of just always true by the nature of its logical structure, because it's an equation with the same thing on the left and the right. Okay, so this is the simplest kind of universal validity. And one of the questions of first order logic is, you know, what are the universal validities? How can we characterize our universal validities? Then this is kind of a question. How can we characterize universal validities? I mean, it's useful to know if something is universal validity, because, you know, if you give me something and say it's universal validity, I know it's going to be true everywhere. Right? Maybe there's an algorithm for checking whether something is a universal validity. Right? You could hand me a formula, and maybe I've got an algorithm up my sleeve or computer program. I could just plug in this formula and it'll give me a yes, no answer as to whether it's a universal validity or not. So by algorithm, I mean just something, you know, computer procedure, program, process, whatever. This is often called an effective procedure. Slightly old-fashioned word from earlier days, before Turing, before there was the idea of a computer or computer program. But in essence, what they were talking about was, you know, something that was like an algorithm, right, for determining, for checking whether a formula is a universal validity. Okay, entirely reasonable questions that we will be answering. So we shall answer these questions. Okay. This is just an alternative piece of jargon that people always talk about. If phi is an L sentence, that means no free variables, so we don't have to worry about assignments. M is a structure appropriate for the language. M is a model of phi, means phi comes out true in M under any assignment. Well, we don't need assignments because there are no free variables to assign, so we just drop the W's here. So for sentences without free variables, we write this without the W if it's true in M. Right, so any equation here is going to come out true in M. Right? By the definition of what this double turnstile thing is. If gamma is a set of sentences and all of the objects in gamma, all the sentences in gamma are true in M, we say M is a model of gamma. So again, this is just about nomenclature. We say a formula is satisfiable if there is a structure and evaluation which makes it come out true in M. So somewhere the formula can be made to be true. Perhaps by choosing M and W carefully, I can make phi come out true in that structure. So somewhere in the world there is a structure that will satisfy the formula with a particular assignment. Otherwise, it's unsatisfiable. And D is just the counterpart of C, where we take a whole set of formulae rather than just one. So to say a set of formulae is satisfiable says there's a structure and one valuation that makes them all true, all simultaneously for the one assignment. And if that can't be done, we say it's unsatisfiable. So C is just a special case of D, which talks about one formula. So the difference between B and C is B talked about sentences and C talks about formulae. And here we can extend this notation. So we're going to say if I've got a set of formulae, gamma together with phi, I'll use this double turnstile notation. We'll put gamma to the left and phi to the right. So what this is going to mean is any structure and valuation, if it makes gamma come true, it must make phi come out true. Right? So it's quantifying over all possible structures and valuations. Okay? So it's saying for all M and for all W evaluations into M, if for all sigma and gamma, M is a model of sigma when I use the W valuation. If this holds here, then M thinks that W makes phi come out true. So I don't know which is more readable, I think the English, but here it is in mathematical notation. So this is another way of writing this. So for all structures and valuations, if everything in gamma is made true by W, then phi is made true by W. So this is kind of abstracting away from structures and valuations. Okay? It's a relation between sets of formulae. Okay? But it refers to structures out there in the real world. So if you then think about what some of these things mean, suppose gamma is the empty set, then gamma phi, this is really well the empty set, which unfortunately looks a little bit like phi. What is this saying? Well, actually, there is no condition here because there are no sentences in gamma to worry about. So this would say, for all structures and for all valuations, if they make, given a structure, for all structure and for all valuations, if they make everything in the empty set true, then they make phi true. But the left-hand side always happens because there's no condition there. There's nothing in the empty set to worry about. So this is saying, it's almost as there's nothing there. Right? It's just saying all structures and all valuations make phi true. So we drop the empty set and we just write that. So this holds if phi is universally valid. Because we don't have to worry about structures and valuations for the sentences or formulae in the empty set because there aren't any. Okay, a little bit more about that next time.